Today, more examples about fundamental theorem of calculus. In particular, more examples about this formula. Before I present examples, let's take a review about what we learned in the last class. Review number 1. Fundamental theorem of calculus has 2 parts, part 1, part 2. The condition of this theorem is function f is continuous. If function f is not continuous, we don't have fundamental theorem of calculus. Now, part 1. To compute this integral, we need to find one antiderivative of function f. Let me use capital F to denote one antiderivative of f. Then part 1 says that this integral is equal to the value of capital F at the point B minus the value of capital F at the point A. This is part 1. Now, part 2. We have a function f. Take integral on the function f from a number constant a to a variable x. Then this integral, its value depends on the variable x. So this integral is a function of x. Now take derivative on this function. Then the result is the function f. The function f. Review number 2. Essentially, fundamental theorem of calculus says that take integral and take derivative. They are inverse operations. Just like summation, subtraction, they are inverse operations. Multiplication and division, they are inverse operations. E to x and natural log, they are inverse operations. So essentially, fundamental theorem says that integration means take integral. And differentiation means take derivative. These two operations are inverse operations. In detail, okay. We have a function f. Now, take derivative on the function f. To undo the derivative and recover the function f, what we can do? We can take integral from some number to some variable. Okay. Now, this integral by part 1. How to find this integral? Find one antiderivative of this guy. Antiderivative of this guy is the function f, right? Take derivative on this guy, we get this guy. So this guy is antiderivative of this guy. Now plug in x, the upper limit in t, plug in the lower limit in t, and then make a difference. This is this integral. Function f, take derivative, then take integral. Integral cancel derivative. So the original function is here. Function f is here. So we recover function f by taking integral. How about this? This is just a number, a constant. A is a constant. Function value at a, of course, is a constant. But this is a function. X is a variable. On the other hand, we have a function. Take integral on this function. Integral from a number to a variable. then this integral is a function of x. Take integral on function f. Now I want to undo the integral and recover the function f. Then what we can do? Take derivative. Derivative will cancel the integral and go back to the original function f. This is a part two. So this is why I say that fundamental theorem essentially says that integration and differentiation, they are inverse operations. Okay, now let me present examples about these two formulas, more examples. Example 1, evaluate this integral. Yeah. Then by part one, to find this integral, we need to find one antiderivative of this function. This function looks complicated. Okay, now to find one antiderivative of this function, let me make some tries. Okay. This function looks like in structure. This function looks like 1 over square root of 1 minus something square. So my first try is I try R side. Derivative on R side by formula is 1 over square root of 1 minus x squared. So this and this, they are close in structure, but not exactly. Okay. Here the function, this is 1 minus 2x minus 1 squared. Here just x. Now let me make a second try. Now this time I try R side of 2x minus 1. I try this. Let me compute derivative of this function. Sure, I need to use chain rule, right? I need to introduce a temporary variable u for 2x minus 1. So when I use u, this temporary variable, to denote 2x minus 1, then this function is R side of u. Now chain rule. Take derivative on R side of u. Okay, it is 1 over 1 minus u squared times chain rule. Derivative on u. Yeah, this is chain rule. 2x minus 1 derivative is 2. So I get this. Now this function is very, very close to this function. Just the difference is only on the numerator. The numerator here is 4. Here is 2. Differ by a factor 2, right? These two functions. Okay, now to exactly find the antiderivative for this function, I multiply 2 to the left side and to the right side. Okay. Yeah. Multiply 2 to the left side and to the right side. Then I get 2 times R side of 2x minus 1 is equal to 4 multiplied 2 to this guy. 4 over this. Now this function is exactly this function. So antiderivative of this function is this. Okay, now I have successfully find one antiderivative of this function. Now by formula. Okay. The desired integral. Yeah, integral. The desired integral is antiderivative plot the upper limit 1/4 in x and plot the lower limit 0 in x. Okay, this notation means plug in 1/4 in x, then we get this, minus plug in 0 in x, then we get this. Now calculator. 2 times 1/4 minus 1 is negative 1/4. And this is 2 times 0 minus 1, negative 1. A sine of negative 1/4 is negative pi over 6. A sine of negative 1 is negative pi over 2. So therefore, this integral is 2 pi over 3. The following examples are all about this formula. Example 2. Find the derivative of the function g, where g is this integral. This integral is the net area of the region between 0 and x. X is a variable. So the value of this integral depends on x. It is a function of x. To find derivative of this function, we have 2 solutions. In solution 1, I compute the integral first. After I get the result, I take derivative on the result. By fundamental theorem, to find this integral, we need one antiderivative of cosine. Antiderivative of cosine is sine. Then plug in upper limit x in t, lower limit 0 in t, and then make a difference. Then I get this. Sine of 0 is 0, so this guy is just sine of x. So g, this function is sine of x. Now take derivative on g, then we get cosine of x. Solution 2. We can directly apply this formula to solve the problem. Okay. Take derivative on g. G is this integral, so take derivative on g is take derivative on this integral. By this formula, derivative and integral, they cancel each other. Replace t by x, then we get cosine of x. The 2 solutions, they have the same answer. Now, example 2. Find the derivative of the following 2 functions, f and g. Now, derivative on f first. Derivative on f is derivative on this integral. Yeah, on this integral. Now, by formula, derivative cancels integral. Okay, then replace t by x, so we get this function. Yeah. Derivative of f is this function. Now, we compute derivative on g. Derivative on g is derivative on this integral. This integral. This integral is the net area of the region between 0 and 3. Actually, this is a constant function. It doesn't depend on any variable. It doesn't depend on x. This is the net area of the region between 0 and 3. It is a constant. So derivative on a constant is 0. So the answer of derivative on g is 0. More examples about this formula. Example number 4. Find the derivative of this integral. This integral is the length area of the region between 1 and x to the 4th. So this integral depends on x. It is a function of x. Now compute derivative on this function. I want to use this formula to solve the problem, but this formula requires the lower limit is a constant. The upper limit is just x. In this integral, lower limit is a constant, no problem. But the upper limit is x to the 4th, not just x. So I cannot apply this formula to this derivative. Now, to overcome the difficulty, I need to simplify the upper limit. I use u, this temporary variable, to denote x to the 4th. Then this integral becomes this integral. Still, I cannot apply the formula, this formula to this derivative, because the formula requires here is x and here is also x, the same variable. But in this derivative, the upper limit is u and here is x. They are different. Now to overcome this difficulty, I insert du in the denominator here. Put du here. To cancel this du, I put a du on the numerator. This du and this du, they can cancel each other. Don't forget dx. Put dx here. Actually, this step is the chain rule. Now we have two derivatives, this derivative and this derivative. For this derivative, now I can apply the formula. Okay, by formula, derivative and integral cancel, and plug in u in t here. Then we get this equation. Don't forget, u is a temporary variable. By u, I mean x to the 4th. Now plug in x to the 4th in u. Then I get this equation. Derivative on x to the 4th is 4x to the 3rd. So this is the answer to this question. Example number 5. Find the derivative of this integral. This integral is the length area of the region between side of x and 1. Depends on x. So this is a function of x. Now compute derivative of this function. I want to use this formula, fundamental theorem part 2. In this formula, lower limit should be a constant, but lower limit here is sine of x, not a constant. Now to make lower limit a constant, I switch the upper limit and the lower limit. When we switch upper limit and lower limit, don't forget to add a minus sign, okay? Here, I switch 1 and sign, then I get this. Okay, don't forget to add a minus sign. For this derivative, still I cannot apply this formula. This formula, upper limit should be just x, but now it is psi of x. Now let me simplify the upper limit. Below the upper limit by a temporary variable u, okay, then this integral becomes this integral. Okay, now upper limit is u, but here is x, different. Okay, now to make them the same variable, I insert du in the denominator here. To cancel this du, I put a du here on the numerator. Then move dx here. Yeah, again, this step is the chain rule. For this derivative, now I can apply the formula. Okay, derivative and this integral, they cancel each other, and plug in u in t. Then I get square root of 1 plus u squared. This is the result of this derivative. U is a temporary variable. By u in this example, I mean psi of x. Plug in psi of x in u, then I get this equation. Derivative of psi is cosine. So therefore, the answer of this problem, derivative of this integral, is this one. This is the answer. Example number 6. Find the derivative of this integral. This integral is the red area of the region between 1 minus 2x and 1 plus 2x. The region depends on x. So this integral depends on x. It is a function of x. Now, I want to compute the derivative of this function. Again, I want to use this formula, fundamental theorem, part 2, to solve this problem. But this formula requires the lower limit is a constant. So I need to make the lower limit of this integral into a constant. Okay. To do so, I arbitrarily pick a number, say, pick 0, and split this integral into the integral from 1 minus 2x to 0, plus the integral from 0 to 1 plus 2x, Okay, for the second integral, the lower limit is a constant now. But for the first integral, lower limit still depends on x, not a constant. But I can switch the upper limit and the lower limit for this integral by adding a minus sign. So I get this equation. Now, both integrals, their lower limits are constant now. Okay. This is a function. It is a sum of two functions. Then take derivative. By summation formula, this is equal to derivative of the first function plus derivative of the second function. Summation rule. Okay, now we have two derivatives to compute. We need to compute this derivative and this derivative. I want to use this formula. But this formula requires the upper limit is just x. In these two derivatives, upper limits are not just x. So I simplify the upper limits, the two upper limits. For this upper limit, I denote it by u, a constant, a temporary variable. This upper limit, I denote it by w, also a temporary variable. Then I have this equation. Okay, for these two derivatives, still I cannot apply this formula because this formula requires upper limit, and here the two variables should be the same variable, but this derivative here is u, but here is x. Here is w, here is x, they are different. Now, this step is chain rule. I insert du here, du here, du. And then to cancel this du, I put a du in the numerator. And then move the dx here. Do the same for the second derivative. I insert dw here, dw. Then to cancel this dw, I put a dw on the numerator and move this dx here. Now, for this derivative here, from here to here, for this derivative, apply the formula. Derivative and this integral cancel and plug in u in t here. Then I get u times psi of u. This is the result of this derivative. And similarly, d over dw and integral from 0 to w, this derivative. Apply the formula, then I get w psi of w, right? Cancel derivative and this integral. Plug in w in t, then I get this. Yeah. Okay, now w and u, they are temporary. Now for u, what is u? U is 1 minus 2x. Now I plug in 1 minus 2x in u here. Then I get this equation. W, 1 plus 2x is w. I plug in 1 plus 2x in w here. Then I get this. Okay, now derivative of 1 minus 2x is negative 2. Derivative on 1 plus 2x is positive 2. Simplify this result a little bit, then I get this function. This function is derivative of this integral. Yeah, this is this exactly. So this function is the answer to this problem.